Hi, my name is Jagan MJ. I am pursuing my BTech at IIT Madras in electrical engineering. So today I'm going to take a short theory on the topic photonics and its application and what it is all about. So, what is photonics? Photonics is a branch of physics and technology that involves the study and application of photons, which are particles of light. So basically, for what photonics is that it is basically the study of light and its applications. So whatever we can do with light, it all comes under photonics. Now, it encompasses the generation, detection, manipulation, and transmission of light and other forms of radiant energy, whose quantum unit is the photon. So we all know that photon is the fundamental unit for light. So what photonics is all about is the generation, detection, manipulation, transmission of these small units called photon. Photonic plays a crucial role in a wide range of technologies and applications, impacting fields such as telecommunication, medicine, manufacturing, imaging, and more. So there's a huge and wide application for this photonics in our daily life. And some of them are telecommunication, medicine, and etc. etc. So now we'll look at the origin of photonics. So the word photonics is derived from the Greek word photos meaning light. Maxwell's equation. So we all know that Maxwell has already given us some four fundamental equations which govern the electromagnetic behavior of light. So James Clerk Maxwell formulated a set of equations that describe the behavior of electric and magnetic fields. So those are the four fundamental equations which are given by Maxwell that describe the electromagnetic nature of light. Now, quantum theory. The development of quantum theory in the early 20th century with contributions from scientists like Max Planck and Albert Einstein further advanced the understanding of light as a discrete package of energy called photons. So Max Planck is a scientist who gives the relation E is equal to h nu. That is the energy is equal to h nu, where h is the Planck constant and nu is the frequency. And Albert Einstein also put forward that the energy is in the form of photons, which are in the form of discrete packets of energy. So after the Maxwell, the major advancement in the photonics came from the quantum theory, which was given by Max Planck and Albert Einstein. Next, invention of the laser, 1960. Arthur Schwallow and Charles Townes, building on earlier work by Gordon Gould, developed the theoretical principles for the laser. So, after the quantum effect, the major advancement in the photonics came from the laser. We know what is a laser. Laser is a focused beam of light, and we know the laser. What's the full form of the laser is that it's a light amplification of stimulated emission radiation. So, after the major quantum theory, the major advancement came from the laser. Okay, so now this picture tells us that ray optics is encompassed by wave optics. Wave optics is further encompassed by electromagnetic optics, and electromagnetic optics is further encompassed by quantum optics. So this means that ray optics, we cannot explain the whole nature and study of light entirely by ray optics. So ray optics is the study of light in which dimension or wavelength of the light is very small compared to the dimension of the aperture of the object. So all the nature of light cannot be explained by ray optics. So we need a higher form of study which is wave optics or electromagnetic optics or quantum optics. So wave optics can entirely describe the nature of light in the ray optics also. So every phenomenon in the wave optics cannot be any phenomenon in the wave optics cannot be entirely described by the ray optics. Similar comes from the electromagnetic optics. All the nature of the electromagnetics cannot be explained by wave optics. So in general, every nature of the light can be explained by quantum optics, which encompasses everything that is ray optics, wave optics, electromagnetics. So as a whole, ray optics is a subset of the wave optics, Wave optics is a further subset of electromagnetic optics, and electromagnetic optics is the subset of quantum optics, where quantum optics is the universal set, if you want to tell as a set theory. So, ray optics. Ray optics, also known as geometric optics, is a branch of optics that describes the behavior of light in terms of rays. So, in this ray optics, we treat light as rays. That is, they are traveling in a straight line. They are not bending, they are just traveling from one point to another point through straight line. It is based on the assumption that light travels in straight lines through transparent media, and it focuses on the study of the paths of these light rays. So, as I told you before, the light travels in a straight line. We do not discuss about any other nature of light. It's just that light travels in a straight line. Ray optics is particularly useful when dealing with situations where dimension of optical elements are much larger than the wavelength of light. That is, as these lights pass through the object, the wavelength of the light is very small compared to the dimension of object. This is to ensure that there do not we do not entertain any bending of light. If the dimension of the object is nearly equal or it's near to the wavelength of light, then there might occur some bending of light, in which the study of light can only be explained by wave optics. So ray optics is the study of light where light light travels in straight line. So we have all learned in our previous classes like what are the basic phenomena for the ray optics. So reflection, the study of how light rays change direction when they encounter a reflecting surface. The law of reflection states that angle of incidence is equal to the angle of reflection, and both angles are measured with respect to the normal, a line perpendicular to the surface at the point of incidence. So what basically reflection is that when the light hits or imparts or on a smooth surface called a mirror, then the light will reflect at an angle which is equal to the incidence. So angle of incidence is equal to angle of reflection, and the whole thing, that is the normal, the plane of mirror, all lie in the same plane. So reflection. So next, refraction. Refraction refers to the bending of light rays as they pass through the different optical media with varying refractive indices. So refraction only occurs when the light rays hits on a interface of two media where the refractive indices are different. Snell's law describes the relation between the angle of incidence and refraction and the refractive indices of the media involved. So to mathematically put forward what is refraction, Snell has already given his law called Snell's law, that is n1 sine theta 1 equal to n2 sine theta 2. That is, let's take n1 as the medium in which light was traveling, that is the first media. N2 is the second media in which the light is going to hit at the interface. Theta 1 is the angle of incidence for the media 1, and theta 2 is the angle of refraction for the media 2. So n1 sine theta 1 equal to n2 sine theta 2. That is the Snell's law. For the reflection case, it's nothing much. Theta incidence equal to theta reflection. That is, the angle of incidence is equal to angle of reflection, and all the thing, angle of incidence, angle of reflection, the normal, the plane of the mirror, all lie in the same plane. So now let's look at the figure for the ray optics. So we can actually see a mirror and a focused beam of light which is hitting on a mirror, and the light rays getting reflected. So the angle of incidence theta is equal to angle of the reflection theta dash. So that is all about the reflection law for the ray optics. We can also see that all the things, that is the incident ray, the reflected ray, the normal, and the mirror, all are in the same plane. So normal is nothing but an imaginary line we are supposedly taking at the point of incidence which is normal to the mirror. So theta incidence equal to theta reflection, or theta E equal to theta R for the reflection from a surface of a mirror. So that's all for the reflection law. Now let's see. Now let's see for the Snell's law. So we can actually see two media. In this case, we are taking first media as air, second media as water. So the refractive index for the air is approximately 1, and for the water it's 1.33 or 4 by 3. So we are seeing an incident ray which is which is hitting on the interface of the two media, that is air and water. So what happens is that the refractive index of the air is 1, refractive index of water is 1.6, that is water is a denser media compared to air. So what happens is that when the light rays hit at the interface, the velocity of the light rays slows down in water because its refractive index is higher. So what happens is that as a result that the velocity of light slows down, it bends towards the normal. So the light rays bend towards the normal, so that the angle of incidence is not equal to the angle of refraction. So the mathematical equation that governs this is n1 sine theta 1 equal to n2 sine theta 2, where n1 is the, for in this case n1 equal to 1, n2 equal to 2, n2 equal to 1.33. So for example, if you are taking theta 1 equal to 40 degree, then we can actually find from the equation that theta 2 equal to sine inverse of n1 sine theta 1 by n2. So angle of refraction is going to be lesser than the angle of incidence if light rays travel from rarer media to denser media. If it travels from denser media to rarer media, then the angle of refraction is going to be more than the angle of incidence. So this only happens if you have a two media with different refractive indices. So Snell's law gives us the mathematical expression for how the refraction occurs. Total internal reflection. Total internal reflection, also known as TIR in short form. So total internal reflection is an optical phenomenon that occurs when light traveling within a media strikes on the boundary with another medium at an angle greater than the critical angle. So what this total internal reflection is that when light travels from denser media to rarer medium, and when it hits the interface of these two medium, there might occur the chance for total internal reflections. And this, if this total internal reflection is supposed to happen, then the angle of incidence at the point of incidence should be greater than the angle called critical angle. So let's see what this particular critical angle is all about. So in this situation, instead of being transmitted into the second medium, the light is entirely reflected back into the first medium. So in the case of total internal reflection, instead of the light ray going to be refracted, this light ray is going to be reflected back into the same medium. So instead of getting refracted, it is going to be reflected, even though some light rays are going to be refracted too, but we are negliging this case. Total internal reflection is a crucial principle in optics and has practical applications in various optical devices. So we all know that we in today's world we use fiber optics, right? So light actually travels in the fiber optics with the principle for total internal reflection. That is, when the light rays, it travels inside the fiber. So this fiber has a core and a cladding. So when the light rays in the core travels, it ensures that the angle of incidence is greater than the angle of critical angle. So if this happens, then the light rays is going to be reflected rather than be refracted. So total internal reflection is happens only when the particular angle is greater than the critical angle, and critical angle is different for different mediums. Okay, okay. So now let's see what this particular angle called the critical angle is all about. So critical angle. The critical angle is the angle of incidence at which light is refracted at an angle of 90 degree. That is, it just grazes along the boundary between the two media. So what this critical angle is that when the light rays travel from a denser media to rarer media, we know that the velocity of light inside the denser media is going to be lesser than the velocity of light in the rarer media. So when light hits the interface of these two media, then light rays is going to bend away from the normal. So critical angle is such an angle such that the refracted ray is perpendicular to the normal at the point of incidence. So what it means is that the light rays which are refracted just grazes along the interface of the two media. So that is, it is at an angle of 90 degree. So that is the particular critical angle for two medias. Conditions for total internal reflection. Total internal reflection occurs when light travels from a medium with a higher refractive index to a medium with a lower refractive index. So that is the first condition. That is, light rays should travel from a denser medium to rarer medium. Else, there is not going to be any condition for the total internal reflection. And the second condition is that like the angle of incidence should be greater than the angle of critical angle. So if the angle of incidence is equal to the critical angle, then the light rays is going to just graze along the interface, which is not what we need. We need actually the light rays to travel inside the fiber, right? So angle of incidence is going to be greater than the angle of critical angle. Only then total internal reflection would happen. So these are the two conditions, that is the light rays should travel from denser media to rarer media, and also the angle of incidence is going to be greater than the critical angle. So critical angle is just that the angle at which the light rays when passes from the denser medium to rarer medium, the refracted ray just grazes along the interface, that is the angle of refraction is equal to 90 degree. Okay, let's see this figure what total internal reflection is all about. So we can see a light rays coming from inside the water towards the air. So we know that water is a denser medium and air is a rarer medium. So when light travels inside the water through the air, the velocity of light in water is lesser than the velocity of light in air. So when it hits the interface, then the velocity of the light will be higher compared to that of the water. So what happens? The light rays bends away from the normal. So it happens such that the critical angle is such that the angle of refraction, that is the when the light is bent away from the normal, such that the angle is 90 degree. So in this example, we can see the incident ray from the water. It gets reflected at the point of incidence for the two media, air and water. So we should ensure that light should travel from denser media to rarer medium to occur total internal reflection. So from Snell's law, we can write n1 sine theta 1 equal to n2 sine theta 2. Here n1 is the refractive index for water, n2 is the refractive index of air, theta 1 is the angle of incidence inside the water, theta 2 is the angle of refraction. For critical angle, we are going to take theta 2 equal to 90 degree. So n1 sine theta 1 equal to n2 sine 90. That is n1 sine theta 1 equal to n2 sine 90. So n1 sine theta 1 equal to n2 theta 1, that is critical angle. Let's denote critical angle as theta c. So theta c equal to theta 1 equal to sine inverse of n2 by n1. So obviously n2 is greater than n2 is less than n1. So theta c is going to be a value which is between 0 and 90 degrees. Fiber optics. In optical fiber communication, which involves guiding light waves, the structure often consists of a core and a cladding. So in our day-to-day life, we use fiber optics, right? So this fiber optics has two components called core and cladding. The core comes inside the cladding such that the cladding is at the cladding acts as a wrapper or a cover around this core. So this fiber optics consists of two components called core and cladding, which we use in our day-to-day life. So let's see what this core and cladding is about. Core. The core is the central part of the optical fiber through which light is guided. So the core, it is a part of the fiber optics where light actually travels. It has a higher refractive index than the surrounding cladding. So the refractive index of the core is higher than the cladding. This is to ensure that total internal reflection happens, because the first condition for the total internal reflection is that light should travel from denser medium to rarer medium. So obviously the refractive index of the core should be larger than the refractive index of the cladding. The refractive index difference between the core and cladding is crucial for the phenomenon of total internal reflection, which allows light to be guided along the core. So obviously the refractive index of the core and cladding will contribute to the angle of critical, that is a critical angle. Now cladding. The cladding surrounds the core. That is the cladding acts as a wrapper or a cover around the core. This is the part of the fiber optics in which light doesn't travel, but it is crucial for the total internal reflection to happen. It serves to confine the light within the core by ensuring that the total internal reflection occurs at the core cladding interface. So, cladding is the part where light doesn't travel, but it is a necessary part of the fiber optics where total internal reflection needs to be happen. Then cladding is there. The cladding material is chosen to have optical properties that help in the light guiding process. So, cladding has a lower refractive index compared to the core, such that when the light travels from denser to rarer, total internal reflection happens. Like it should happen only when the angle of incidence is greater than the particular critical angle for the two mediums. Okay, now let's see what this figure is about. So this is a cylindrical waveguide or a fiber optic in which core has a refractive index called N1, cladding has a refractive index N2. So obviously N1 is going to be greater than N2, because for the TIR or total internal reflection to happen, the refractive index of the core should be higher than the refractive index of the cladding. So in this figure, they are given A as the radius for the core and B as the radius for the cladding or the cylindrical waveguide. So we can see that actually in general what we use for the core is that we use a mixture of SiO2 plus GO2, that is silicon dioxide and germanium dioxide, and we also have a cladding which is basically silicon oxide. So this is how a particular cylindrical waveguide looks like that we use in our day-to-day life for the transmission of light. That is, we use fiber optics, right, for the light transmission. So this is what it actually looks like. So the refractive index is going to be of the core should be greater, and also the angle of incidence should be greater than the angle of critical angle, else light won't travel inside the core and we won't get the result what we want to get. So we actually discussed about fiber optics, right? So now let's discuss about what this numerical aperture is about. So the numerical aperture Na stands for numerical aperture, is a dimensionless number that categorizes or that characterizes the range of angles over which a fiber optic or microscope lens system can accept or emit light. It is a critical parameter in optical systems, especially in microscopy and fiber optics, as it determines the system's ability to gather and focus light. So we saw that angle of incidence should be greater than the critical angle for the TIR to happen. But we also know that there's going to be a source of light, right? So it's going to enter the fiber optics at some angle, right? So in order for this TIR to happen, we also needed to ensure what's the numerical aperture is also about. So numerical aperture also plays a crucial role in the transmission of light inside the fiber. So this this is a quantity which doesn't have any unit. So for the like sometimes when the light, if it incident on a fiber, so if the TR is going is supposed to happen, then there's going to be some condition for the light to be incident on the fiber optics from the external media. Okay, so let's see in the figure. So it's given theta c is the critical angle, theta c bar is equal to 90 degree minus theta c, and it's also given the acceptance angle given as theta a. So suppose let's say that light enters the fiber optics at an angle theta a. So let's say that the medium is air, the external medium is air. So n1's like refractive index of air into sine theta equal to the refractive index for the core is going to be n1, right? So refractive index of air is 1. So 1 into sine theta is equal to n1 sine theta c bar. Okay, so 1 into sine theta equal to n1 sine 90 minus theta c. That is uh, 1 into sine theta equal to n1 into cos theta c. Also from the core cladding interface, we know that angle of incidence, like when angle of incidence is equal to angle of critical angle, n1 sine theta c equal to n2 sine 90, where 90 is the angle of refraction, right? So n1 sine theta c equal to n2. So from this equation we get that n1 sine theta c equal to n2. From the other equation we get that 1 into sine theta equal to n1 cos theta c. From these two equations we can write sine theta equal to n1 into root of 1 minus cos theta c bar the whole square. That is equal to n1 into root of 1 minus n2 by n1 the whole square. That is, when n1 comes inside the root, it comes equal to root of n1 square minus n2 square. That is, sine theta equal to root of n1 square minus n2 square. So theta equal to sine inverse of root of n1 square minus n2 square. So numerical aperture in a mathematical formula is equal to root of n1 square minus n2 square, and theta is the acceptance angle. So this acceptance angle is also a crucial part for the light to make sure that the light inside the core travels with TIR condition. So if the light rays is going, like if the light rays were supposed to be at an angle which is greater than the acceptance angle, then light rays won't ensure TIR. So we need to make sure that all the light rays which comes inside that theta A, that angle, right? So inside that cone, if the light rays are bound to be inside the cone, then it makes sure that the light rays is going to travel along the core and TIR is supposed to happen, and the light ray is going to be traveling along the fiber. So numerical aperture is given by root of n1 square minus n2 square, and the acceptance angle, that is theta A, is equal to sine inverse root of n1 square minus n2 square, or sine inverse Na, that is Na is numerical aperture. Okay, so now in this figure it's given that for the small, for a fiber optics having small numerical aperture is going to be having a small cone right at the interface. For a fiber optic having large numerical aperture is going to be having a large cone. Large cone means that the angle of cone is higher compared to the smaller one. So this large, this fiber optic having a large numerical aperture, right? So in medical field we have endoscopy, right? So this endoscopy is to be made to be ensured such that it should have a large numerical aperture, because light rays from the surrounding should be able to travel inside the fiber so as to get a clear view. So in this case, for that particular use, we need a larger numerical aperture. So for larger numerical aperture, we know that numerical aperture is equal to root of n1 square minus n2 square. So for larger numerical aperture, it's obvious like root of n1 square minus n2 square should be larger. So n1 square minus n2 square should be larger. That is, n1 should be larger than n2. So for larger numerical aperture, n1 should be larger than n2. We obviously know n1 is going to be larger than n2, but for larger numerical aperture, n1 should be higher, like a bit higher than n2 for compared to the fiber optic having smaller numerical aperture. So by manipulating the refractive indices for the core and the cladding, we can actually manipulate the acceptance angle, or acceptance angle is also given like acceptance angle or numerical aperture. So by manipulating the values, we can actually design a fiber optic, like whether we should have a fiber optic having a smaller numerical aperture or a fiber optic having a larger numerical aperture by manipulating these two values. Okay, so attenuation coefficient. The attenuation coefficient is often denoted by the symbol alpha. Is a measure of the rate at which the intensity of a wave decreases as it propagates through a media. So attenuation is given like the intensity of the light is going to reduce as it travels along a media, and this mathematically this attenuation is given by the attenuation constant called alpha, which gives the rate like how the intensity of the light is going to decrease as it propagates through the media. It is a crucial parameter in various fields, including physics, acoustics, optics, and telecommunication. The attenuation coefficient is often is used to describe how quickly a wave's energy diminishes with distance or time. So mathematically, this attenuation coefficient will tell you how the intensity or how the strength of the light is going to diminish as it travels through the fiber or through a particular media. So for this attenuation, like if we are given the, let's say we are given two powers, that is the input power is given and also the output power at a certain distance as the light travels, and we can actually find the loss in dB scale. That is, loss in dB scale is equal to 10 log power input by power output. So that is the equation that we can get as the loss in dB. So alpha is the attenuation constant, and it mathematically represents how the wave diminishes its intensity as it propagates through the media. So in the previous slide, we have discussed about um, fiber optics, right? So we actually see how we can manipulate the values for N1 and N2 and have a higher acceptance angle or higher numerical aperture. So let's see what the single and multi-mode fiber is all about. Single mode fiber, SMF, like SMF stands for single mode fiber, and multi-mode fiber, MMF, that is multi-mode fiber, are two types of optical fibers used in fiber optic communication systems to transmit data over long distances and short distances respectively. So these are the two types of modes that we actually use for the transmission of light inside a fiber optic. The primary difference between the lies in the size of the core through which light travels. So if the size of the core is lesser than, which means that only some modes or a single mode is going to travel. So the size of the core is going to tell us what mode the fiber is. Model dispersion is more significant in multimode fibers due to the multiple paths that light can take through the larger core. It results in spreading of the light pulses and limits the achievable data rates and distances in multimode system. So, what is model dispersion? Model dispersion happens only when there is more than single mode. That is, if a fiber optic supports more than one mode, then This light rays can travel in many directions, right? So in such a case, it results in the spreading of light. So modulated dispersion is actually the spreading of light as it travels through the fiber. So model dispersion, it happens mostly in MMF, that is multimode fiber. And also the size of the core tells us about what modes the fiber can support. If the size of the core is lesser, then mostly less number of modes or single mode is going to be supported. If the size of the core is going to be large, then many modes can support in the fiber. Okay, now let's see in the figure. You can see step index MMF, that is step index multimode fiber. SMF, that is single mode fiber, and also GRIN MMF, that is graded index multimode fiber. So in the case for step index multimode fiber, obviously in the name it has multi-mode. So this particular fiber optic supports a variety number of modes, that is the fiber optic supports more than one mode. So in this case model dispersion can happen, that is the light rays can spread and travel in different directions in such a way that the intensity that the light is going to give at the output is going to be lesser. SMF, you can actually see that the size of the core for the SMF is less compared to the size of the core for the multi-mode fiber. In single mode fiber, only single mode is supported, right? So there's not going to be any spreading of light, and also there's not any like anywhere, like there's not going to be any spreading of light, and also there's not going to be any directions apart from a single one in which light can travel. So there's no chance for model dispersion. So graded index multimode fiber. So in the case of multimode fiber, we actually see that when there are more than single mode, then light travels, then the light rays can spread, they can travel in different directions in such a way that the intensity of light is going to be lesser at the output. So what this graded index multimode fiber is that the refractive index is going to be higher at the Typically, this particular graded index multimode fiber is such that the refractive index of the core is going to be larger, and the refractive index at the boundary is going to be lower in such a way that the model dispersion can be reduced. So refractive index is higher at the center and refractive index is lower at the outer part. So model dispersion is avoided, or there would have less model dispersion. Okay, so we discussed about fiber optics, right? So let's see what this V parameter is. So the V number of a fiber, also known as the V parameter, is a dimensionless quantity used in the context of optical fibers. So V is a dimensionless quantity, and it tells how many modes can a particular fiber optic support. So this V number, V number is given by 2 pi a by lambda into numerical aperture. That is, a is the radius of the core, N is the numerical aperture, that is root of n1 square minus n2 square. Lambda is the particular wavelength of light in which wavelength of the light which travels through the fiber optic. So A and lambda have the same dimension. So this V number is a dimensionless quantity. It is a crucial parameter which tells how much or how many modes can a fiber support. It is a measure of the mode confinement within the core of the optical fiber and is commonly associated with multimode fibers. So this V number tells us how many modes can a fiber optic support. So we know that for a single mode fiber, only single mode supports. So this V number is doesn't have any significance. So V number has significance only where fiber supports more than a single mode. That is, it V number is more crucial or significance for multi-mode fiber or MMF. The V number helps characterize the model behavior of light propagation in the fiber. So this V number is going to be telling how much model dispersion is going to be there, because This particular beam number is give you how many modes can the fiber supports, and if the number of modes that the fiber supports is higher, then there's going to be a lot of model dispersion because there's going to be a lot of spreading, and also there's going to be different directions in which light is going to travel in such a way that the intensity of the light that we receive with the output is going to be less compared to the light which has been transmitted initially. So V number is a crucial dimensionless quantity which tells us how much model dispersion is going to happen or how many modes can a particular fiber optic support. Okay, so in the figure we can see B equal to 2 pi a by lambda into Na, where Na is the numerical aperture or Na equal to root of n1 square minus n2 square. A is the radius of the core, lambda is the wavelength of light. So A and lambda is the wavelength of light. So these two quantities have the same dimension. So they cancel out each other. N1 and N2 are the refractive indices which doesn't have any dimension. So V number is going to be a dimensionless quantity. N is equal to root of n1 square minus n2 square. That is the numerical aperture for the core cladding fiber optic. In the graph, we can see that for particular value of V, it's going to be single mode, and it's going to be in for other is going to be multi-mode. We can actually see an imaginary line passing through the point between 2 and 3. That is, the value is 2.405. So if we get the V value lesser than the 2.405, then the fiber supports only a single mode. If the value of V is going to be greater than 2.405, then the fiber optic supports more than one mode. So for all the multi-modes, the value of V is going to be greater than 2.405. And for all the single mode fiber, the value of the V parameter is going to be less than 2.405. So this particular V parameter is going to tell us how many modes the fiber can support or how much the model dispersion can happen inside the fiber optic. So for the single mode condition, it's V is less than 2.405. That is, for a fiber optic to support single mode, then the value of V is going to be lesser than 2.405. M equal to 4V square by pi square plus 2. So what this M is the number of modes that a fiber optic can support. So with the help of V parameter, then we can tell what's the value for M is going to be. So for V less than 2.405, the value of M is going to be 1. For V parameter going to be greater than 2.405, the value of M is going to be greater than 1. So from the V parameter, we can calculate what is the M value. That is how many modes can a fiber optic support. For larger values of V, that is when V is very greater than 1, then we can approximate the value, that is M is approximately equal to 4 V square by pi square. This equation is only applicable for the values where it has larger V. So for single mode fiber, the value of V is going to be lesser than 2.405. For multi-mode fiber, the value of V is going to be greater than 2.405. That is, the value of M is going to be greater than 1 for multi-mode fiber. Model dispersion. Model dispersion is a type of dispersion that occurs in optical fibers, particularly in multimode fibers. So, model dispersion only happens in the case where fiber can support more than one mode. That is, if the fiber can support more than one mode, then there are going to be spreading of light, and also light can travel in different directions. So, the intensity of the light that is going to be produced at the output is going to be less compared to the initial light. It refers to the spreading of optical pulses as they travel through the fiber due to the presence of multiple propagation modes paths within the fiber core. So, model dispersion happens because of the spreading and the different directions in which the light can travel because the fiber supports more than a single mode. So model of dispersion only happens in the case for multimode fibers or MMF. Each mode corresponds to a different angle or position at which light can enter the fiber, leading to variations in the path lengths and consequently differences in the time taken for the light to traverse the fiber. So if the we know that there's going to be T mode, TM mode. So T01, T02, T03. So these are all different modes. And for all these different modes, there are going to be different multiple propagation modes. And also all these different modes have different path lengths. And due to different path lengths, there's going to be spreading of light, and also the intensity of light is going to be different at the output. That is, modal dispersion happens in the case for multimode fibers. So wave optics. Wave optics, also known as physical optics or wave theory of light, is a branch of optics that describes the behavior of light using the wave characteristics of electromagnetic radiation. This approach contrasts with ray optics, which treats light as a collection of rays that travels in straight line. So, in this wave optics, we are going to treat light as a wave rather than a ray of light. So, all the properties of ray optics can be explained by wave optics, but all the properties of the wave optics cannot be explained by ray optics. That is, ray optics is a subset of wave optics. Wave optics is particularly useful for explaining phenomena that involve interference, diffraction, and polarization. So, wave optics can tell us what this diffraction, interference, and polarization is. These phenomena cannot be explained by a ray of light by treating light as a ray or a straight line. This can only be explored or understand with the help of treating light as a wave. So wave optics is going to be a superset of ray optics, and all the phenomena of the ray optics can be explained by wave optics, but vice versa it's not. Diffraction of light. Diffraction is the bending of waves around obstacles and spreading of waves when they pass through openings. So why we can explain the properties of light with the wave is that when the wavelength of the light is much comparable compared to the size of the obstacle, then the ray optics fails to explain these phenomena. So what happens in diffraction is that light waves actually bend around these obstacles where the dimension is much comparable to the wavelength of light. So diffraction is the bending of waves as the light rays travels through the obstacles having similar dimensions. Diffraction patterns depend on the wavelength of light and the size of the aperture or obstacle. So diffraction. So light is having different wavelength, right? So light is composed of seven colors, right? VIB, GY, OR, violet, indigo, blue, green, yellow, orange, red. So all these different colors have different wavelength. So comparing to different wavelength, these particular light will bend at different angles, compared different angles in corresponding to the wavelength. So diffraction patterns that we get if we place a screen in front of the incident light is going to be different, because these patterns arise because there is a difference in the wavelengths of light. And now let's see what this diffraction is all about. So diffraction of light is a phenomenon that occurs when light encounters an obstacle or aperture with dimensions comparable to the wavelength of light. It involves the bending or spreading of light waves as they pass around the edges of an obstacle or through an aperture. Diffraction is a wave phenomena. We know diffraction can only be explained by wave, it cannot be explained by ray optics, and is a result of interference of light. So diffraction is a result of interference phenomenon. So we all know that Huygens principle. Christian Huygens is a famous scientist which actually told that we can actually treat light as a wave. So Huygens principle states that each point on a wavefront can be considered as a secondary source of spherical wave. The interference of the secondary waves give rise to diffraction pattern. So the interference phenomenon is actually giving rise to diffraction patterns. So in some points there's going to be this light waves is going to add up, that is the intensity is going to be higher. In some waves this light going to be subtracted, that is these light are going to be cancelled, that is the intensity of light is going to be minimum. So for diffraction we have single slit diffraction. When light passes through a single nanoslit or aperture, it produces a diffraction pattern consisting of a central bright fringe. So this particular central bright fringe is having a path difference of 0. That is, when this light is having path difference 0, then this light intensity is going to be added up, that is having a maximum intensity, surrounded by alternating dark and bright fringes. So in either side of the central fringe there are going to be dark and bright fringe. The pattern is characterized by a central maximum and side lobes. So this central maximum is going to have the maximum intensity, that is having a path difference of 0, and in either side there are going to be dark and bright fringes or side lobes. Then we have double slit diffraction. Diffraction also occurs when light passes through two closely spaced slits, double slit, or we know it's famously known as Thomas-Ring double slit diffraction. The resulting pattern includes not only interference fringes but also diffraction patterns within each fringe. Then we have grating diffraction. A diffraction grating, which consists of multiple slits or rollings, produces a complex diffraction pattern with multiple orders of bright and dark fringes. Gratings are often used in spectroscopy. So this particular grating diffraction is used in spectroscopy. Refraction limit. Diffraction places a fundamental limit on the ability to resolve fine details in an optical system. The diffraction limit is a consequence of the wave nature of light and sets a limit on the smallest resolvable feature in imaging system. Fraunhofer and Fresnel diffraction. These are the two popular diffractions. So Fraunhofer diffraction occurs when the light source, diffraction element, and observation screen are effectively at infinity at each other. Fresnel diffraction occurs when the source and or observer are at finite distance from the diffraction element. Angular dependence. The diffraction pattern depends on the angle of observation, the wavelength of light, and the size and shape of the diffracting element. Diffraction grating equation. For a diffraction grating, the condition for constructive interference is given by the grating equation m lambda equal to d sine theta, where m is the order of the fringe, lambda is the wavelength of light, d is spacing between grating rollings, and theta is the angle of observation. Application. So that the diffraction is having a wide variety of applications. Diffraction plays a crucial role in various applications, including the design of optical instruments, the study of crystal structures using X-ray diffraction, and the production of diffraction gratings for spectrometry. Limitations of ray optics. We are using this wave optics because some phenomena cannot be explained by ray optics. So diffraction becomes more prominent when dealing with small apertures and they are not considered in traditional ray optics, which because traditional ray optics cannot explain the phenomenon of diffraction. In situation where wave effects are significant, that is, the aperture or the dimension of the obstacle is comparable to the wavelength of light, diffraction must be taken into account. Diffraction is a fundamental phenomenon in optics that provides insights into the wave nature of light and has practical implications in various scientific technological applications. Understanding diffraction is crucial for optimizing the performance of optical systems. Interference of light. Interference occurs when two or more waves overlap. So these waves can overlap in such a way that they are going to be added up positively. That is, there is no phase difference, then the intensity of the wave is going to be higher. If there is a phase difference between the two waves, then these waves are going to add up in such a way that intensity is going to be lesser than the maximum intensity. Constructive interference occurs when waves are in phase and reinforce each other, leading to increased amplitude. That is, the phase of the waves are zero. That is, there is no phase difference between the waves such that these two waves add up each other having a maximum intensity. Destructive interference occurs when waves are out of phase, resulting in reduced or cancelled amplitudes. So when there is a phase difference between the two waves, then they are going to add up in such a way that there is going to have a resulting intensity which is lesser than the maximum intensity having zero phase difference. Now let's see what this interference is all about. So basically, interference is a light. Difference of light is a phenomenon that occurs when two or more light waves overlap, leading to the reinforcement or cancellation of the waves. Interference is a characteristic behavior of waves and is a consequence of superposition principle. We obviously saw when there is no phase difference, then waves going to add up positively. If there is a phase difference, then they are going to add up in contributing to the phase. So these waves are going to add up with the superposition principle, which states that when two or more waves meet at a point in space, the resultant displacement at that point is the vector sum. That is, vector makes or contributes the phase difference. Vector sum of the displacement of the individual waves. So let's see what are some of the key aspects of difference of light. Superposition principle. Interference is based on the superposition principle, which states that the total effect at a given point is the sum of the effects produced by each individual wave. Coherent sources. For interference to occur, the source of light must be coherent, meaning they have a constant phase relation. That is, the particular light source should be a coherent source which is having a constant phase. Incoherent sources do not maintain a constant phase and their interference patterns are not stable. So, if we are using a particular light source such that it is having different phases in different times, then the interference pattern that we get is not going to be stable. It's going to be unstable because phase difference there is every time there is phase difference. So, if phase difference is always different, then interference pattern is also different always. Constructive interference. Constructive interference occurs when waves arrive at a point in phase. So in phase means there is no phase difference or phase difference is 0, 360, 720 with the same phase. In the case, the amplitude adds up and resulting in a bright fringe or region of maximum intensity. Destructive interference. Destructive interference occurs when waves arrive at a point out of phase. In this case, the amplitudes subtract from each other, resulting in a darker fringe or region of minimum intensity. Double slit interference. One of the classical examples of interference is the Thomas Young's double slit interference experiment. When the light passes through two closely spaced slits, it creates an interference pattern on a screen with alternating bright and dark fringes. Path difference. The key factor in determining the interference is the path difference, the difference in the distance traveled by the light from two coherent sources to a given particular point on the screen. The path difference determines whether waves arrive in phase or out of phase. Interference fringes. Interference produces a pattern of bright and dark fringe on a screen or surface. The spacing between fringes depends on the wavelength of light, the distance between sources, and the angle of observation. Single slit diffraction and interference. Interference also occurs in the context of single slit diffraction, where light passing through a single slit produces an interference pattern. This pattern is a result of waves spreading out after passing through the slit. Michelson interferometer. So let's see what this Michelson interferometer is all about. The Michelson interferometer is an optical instrument that uses interference to measure small changes in the length of an optical path. So this is a particular optical instrument which uses interference to measure small change in the optical path. It has applications in precision measurements such as determining the speed of light. Interference is widely used in various applications such as interferometry for measuring distances, creating interference filters, and producing holograms. Young's experiment involves light passing through two closely spaced slits, creating an interference pattern on a screen. The pattern results from the superposition of waves emerging from the two slits. Understanding the principles of interference is essential in optics and has practical applications in various fields, including physics, engineering, and telecommunication. Interference patterns provide variable and valuable information about the properties of light and the nature of wave behavior. So let's see what Brewster angle is all about. So Brewster angle, also known as the polarization angle, is the angle of incidence at which light with a particular polarization is perfectly transmitted through a transparent dielectric surface with no reflection. This phenomenon occurs when unpolarized light strikes a medium with having a higher refractive indices. In the case of total internal refraction, we see that light should travel from denser to rarer medium. That is, light should hit a medium with having refractive index lesser. For the Brewster angle case, we need to have a higher refractive index. That is, the light should travel from a rarer medium to a denser medium. This phenomenon occurs when unpolarized light strikes a medium with a higher refractive index. So we need a denser medium for the polarization angle. So Brewster angle is also known as the polarization angle, is a specific angle of incidence at which the particular polarization is perfectly transmitted through a transparent dielectric surface with no reflections. So in the case of TIR, we didn't have any refracted or transmitted ray, only reflected ray. For in this Brewster angle case, we are only having transmitted or refracted ray with no or zero reflection. This phenomenon is named after the Scottish physicist Sir David Brewster, who first described it in 1815. Brewster law. So Brewster law relates the Brewster angle theta b. So Brewster angle is denoted by the theta b, where b stands for Brewster, theta is angle. So Brewster angle. So Brewster law relates the Brewster angle theta b, the angle of incidence, and the refractive indices of the two media involved. The law is tan theta b, that is tan of Brewster angle is equal to n2 by n1, where theta b is the Brewster angle, n1 is the refractive index of the first medium, usually air or vacuum. N2 is the refractive index of the second medium. That is, second medium is having a refractive index having higher than the first medium. That is, N2 is the refractive index of the second medium. Polarization effect. At the Brewster angle, light that is incident on the surface is perfectly polarized parallel to the interface. This means that light waves with electric field vectors perpendicular to the plane of incidence are mostly reflected, while those parallel to the plane of incidence are mostly transmitted. So basically the transmitted lines are those which are parallel and the perpendicular are ones which are blocked. For light incident at Brewster angle with polarization parallel to the plane of incidence, there is no reflection. only transmission. For this Brewster angle, we only have transmission or refraction. There is no or zero reflection. The tangent of the Brewster angle is equal to the ratio of the refractive indices of the two media. The relation is based on the geometry of the situation and the requirement that the reflected and refracted waves are mutually perpendicular. The Brewster angle is dependent on the refractive indices of the two media. If the refractive index of the second media increases, the Brewster angle also increases because Brewster angle is, that is, tan theta b is directly proportional to refractive indices. So as the value of refractive indices increases, angle of Brewster also increases. The Brewster angle has practical implications in optics and is often used to minimize reflections in various optical systems. So for optical systems where we denote reflections, we use the case for Brewster angle. Anti-reflective coating on lenses are designed to take advantage of the Brewster angle to reduce glare. Photography and films. Understanding the Brewster angle is important in photography and filmmaking, where controlling reflections is crucial for obtaining clear images. Brewster windows are optical components designed to operate at or near the Brewster angle. They are used in laser systems and other applications to minimize reflections and maximize transmission. Polarizing prisms built on the Brewster effect are used as polarizers in optical systems. In summary, the Brewster angle is a critical concept in optics, providing a means to control and minimize reflections in various optical systems. It is based on the principles of wave optics and the behavior of light at dielectric interfaces.